Welcome to the Deep Dive, your essential shortcut in a world, well, overflowing with information. You know the feeling, right? Keeping up with the relentless pace of tech, especially something as vital as cybersecurity. It can feel like trying to drink from a fire hose. How do you actually cut through all that noise and get to the truly crucial insights, the knowledge that genuinely makes you, well-informed and prepared?
Yeah, that's exactly what we're trying to do here. We're here to kind of distill that information deluge into clear, actionable understanding for you. Consider this your definitive guide, really, custom-tailored to equip you with the insights you need.
Absolutely. And today we're tackling a topic that's, well, more critical than ever, the OWASP API Security Top 10 for 2023. If you're involved in any way with digital services, you definitely know OWASP, the Open Web Application Security Project. They're the recognized authority. And this list, it isn't just some casual overview. It's the most current and authoritative consensus on the critical security risks facing APIs today. It's really the definitive guide for anyone building, developing, or securing the digital infrastructure that frankly powers our lives.
And it's not just theoretical, right? This 2023 edition, which is still incredibly relevant, current as of September 2025, it's built on solid real-world data. We're talking insights drawn from analyzing over 40,000 applications, plus the collective wisdom of security experts worldwide. What's really striking about this list, I think, is how clearly it reflects the rapidly evolving threat landscape specifically for APIs.
Right. So our goal here today, it isn't just to list off these vulnerabilities. We want to dive deep. We're going to unpack how they're actually exploited out there in the wild, the tangible real-world impact they have. And most importantly, what you can actually do right now to prevent them. We want to help you understand the foundational architectural flaws, the implementation mistakes that attackers are increasingly targeting. They're moving beyond simple bugs to, well, more sophisticated manipulations.
And for you listening, this matters hugely because APIs are, quite literally the invisible threads powering nearly everything you interact with digitally. Your banking app, your smart home devices, social media feeds, the back end of your favorite online store APIs are the glue. They're the fundamental connectors. Understanding these risks isn't just for the security specialists anymore. It's crucial for anyone who builds, uses, or frankly just relies on digital services in today's hyper-connected world.
Totally agree. This deep dive is really designed to arm you with practical, actionable knowledge, stuff that enables you to build a proactive, security-by-design posture right from the ground up. Now, it's worth noting, this 2023 list is a pretty significant update from the 2019 version. You'll see vulnerabilities that have been renamed, some have been merged together, and others are entirely new. And that really reflects how attackers' focus has shifted.
Yeah, and what's particularly fascinating about that evolution is the clear strategic shift in attack vectors. It's quite noticeable. We're seeing attackers increasingly targeting the business logic of applications, and the inter-service communication that ties microservices together. It's not just about generic web application flaws anymore. This signals a maturing threat landscape where the focus has moved beyond basic technical errors to understanding and then subverting how digital services interact and, crucially, what business functions they enable.
Right. There's even a minor controversy mentioned in our source material, some debate around GraphQL-specific exploits, things like using batching for authentication bypass. But it's really important to remember that OWASP's approach is fundamentally data-driven. They ensure these rankings are neutral across different API types and stakeholders. They're balancing those debates with what's actually happening out there in the real world.
Exactly. The data really speaks for itself regardless of the specific API technology you're using. And as we navigate through this list today, you'll probably start to see a recurring, almost unsettling theme emerge. Catastrophic failures, the really big breaches, often stem not from these hyper-sophisticated zero-day attacks, but from neglecting basic security hygiene, just the fundamentals. We're talking about meticulous access control, robust inventory management, and what we often call a deny-by-default architectural philosophy.
So what does this all mean for you, the listener? I think it boils down to building a proactive, defense-in-depth approach. It's about designing systems to be inherently secure, right? Rather than just reacting and patching vulnerabilities after they pop up. Are you ready? Let's dive straight into the .1 threat on this critical list.
Absolutely. Let's get into it.
Okay, coming in at #1, and alarmingly retaining its top spot from the 2019 list, is API 1.2023 Broken Object Level Authorization, usually shortened to BOLA. This is described as the pervasive authorization failure. So let's strip away the jargon. What exactly is BOLA, and why does it stubbornly remain the most critical threat facing APIs today?
Well, BOLA is right at the top because it's such a deeply foundational flaw. And Maybe surprisingly, it's often remarkably simple to exploit. At its core, BOLA allows an authenticated user right, someone who is legitimately logged into your system, to access or even manipulate data they are absolutely not authorized to see or change. Think of it like an insecure direct object reference, IDOR, maybe you've heard of that, but specifically within the context of APIs. It's a direct consequence of failing to enforce proper, fine-grained access control right down at the individual object level.
Okay, so when you say object, you don't just mean abstract code things. You're talking about concrete data, like someone else's user profile, or a specific database record, a private file, maybe another customer's financial transaction.
Exactly. Any distinct resource the application can access or manipulate. And BOLA is exceptionally dangerous because of both its ease of exploitation and its potential for just a small oversight to lead to truly catastrophic data breaches. The prevalence is just staggering, affecting over 90% of APIs tested in some studies. It's easy for attackers to exploit and, ironically, often easy to detect if you're specifically looking for it. While the technical impact might be rated as moderate sometimes, the business consequences, we're talking massive data theft, huge regulatory fines, crippling reputational damage that are almost always severe.
Wow, 90% of APIs, that's huge. What is it about APIs specifically that makes DLA so widespread? Why are they particularly vulnerable here?
Well, APIs, by their very nature, inherently expose endpoints designed to handle specific object identifiers.
Hmm.
IDs for users, orders, documents, whatever. The flaw creeps in when an application correctly grants a user access to their own objects, like their own profile, but then critically fails to re-verify those same privileges when that same user tries to access other objects of the same type, simply by changing the ID in the request. The crucial lesson here, really, for architects and developers listening, is that strong authentication just logging in is simply not enough, not even close. Authorization checks must be meticulously granular. They need to be implemented on every single request to protect every individual data object. You just can't assume that because someone's logged in, they're allowed to touch everything.
Okay, that makes sense. So let's get into the nuts and bolts. Given how easy you say it is to exploit, can you walk us through how BOLA is typically exploited in the real world? It sounds like it could be incredibly simple, yet devastating.
It often is deceptively simple, yeah. And that simplicity is what allows for massive automation. So the first step for an attacker is usually just to identify vulnerable API endpoints, the ones that handle these object identifiers. These IDs are commonly found right there in the URI path, maybe in a query string parameter, or sometimes even embedded within the JSON request payload itself. For instance, you might see an API call like AP users 123 profile, where 123 is the user ID.
Right, so if those IDs are predictable, maybe just sequential numbers, an attacker could just change 123 to 124, and boom, if BOLA is present, they're suddenly looking at someone else's private profile.
Exactly. That's the most straightforward manipulation, often called ID enumeration. If the IDs are, say, non-sequential GUIDs or something, an attacker might resort to brute force guessing, or maybe more advanced reconnaissance to find other valid identifiers. But once a vulnerable endpoint is found, this whole process can be automated with really simple scripts. They can scrape millions of records in no time, leading to those massive data leaks we hear about. OWASP itself describes scenarios, like in e-commerce APIs, that might expose something like revenue data for different shops. An attacker could just swap the shop IDs and effectively steal competitor data. And in more alarming advanced cases, similar flaws in automotive APIs have even allowed vehicle identification number, or VIN, manipulation for unauthorized actions, like, remote vehicle control.
Wow, okay, that's genuinely terrifying. That's not just data theft, that's the potentially physical danger. Let's talk about some of those real-world consequences, because BOLA has definitely been behind some truly massive, well-publicized breaches.
Oh, absolutely. The Optus data breach in Australia back in 2022 is a textbook example. It illustrates this perfectly. They had an unprotected, public-facing API endpoint that didn't require any authentication, and tragically, it used easily guessable, sequential customer identifiers. Attackers literally just incremented the IDs 1, 2, 3, 4, and scraped millions of customer records. Catastrophic data exposure. Another stark case is the Accenture data leak in 2021. Here, API endpoints vulnerable to simple ID guessing expose details of around 37,000 clients just by incrementing user IDs in the requests. Even the infamous Capital One breach in 2019, while primarily an IAM misconfiguration issue, crucially involved a misconfigured AWS API that allowed object-level access to S3 buckets via predictable paths, affecting over 100 million customers.
And that 2015 GPAC you mentioned earlier by the researchers Miller and Valasek, where they exploited similar flaws in connected car APIs to remotely control a moving vehicle, that wasn't just theoretical, right? It actually led to a massive recall. the real-world impact is just undeniable, ranging from financial ruin to physical harm.
Absolutely. These cases starkly highlight the severe business impacts. It's not just data theft. It's regulatory fines, massive class action lawsuits, and immense, often permanent reputational damage.
Okay, so given how widespread and frankly often simple these BOL exploits are, it sounds like prevention needs to be truly foundational, baked in from the start. What's the single most critical shift developers and architects need to make to really tackle this number one threat?
The single most critical shift, I'd say, is to adopt a deny-by-default authorization model, specifically at the object level. What that means in practice is implementing robust object-level authorization checks. Your server-side code must verify that the authenticated user's ID actually matches the requested object's owner ID, or that they have some other explicit permission. And this check needs to happen for every single request. This validation belongs squarely in the business logic layer, not just on the front end or client side, because that can always be bypassed by a determined attacker.
Right, so the system should always assume no access unless it's explicitly proven otherwise for that specific piece of data on every single call. Got it. What else strengthens this defense?
Well, beyond that core principle, use non-predictable object identifiers. Ditch those easily guessable sequential IDs. Instead, use things like universally unique identifiers, UUIDs, or globally unique identifiers, GUIDs. This makes guessing IDs computationally infeasible. Then, really embrace the principle of least privilege. Implement fine-grained role-based access control, RBAC, or maybe even attribute-based access control, ABAC. Permissions should be dynamically evaluated based on the user's context, their ownership of the object, maybe some organizational hierarchy. For example, if you're using Node.js, you could use middleware, perhaps, like ExpressJWT, that automatically extracts user IDs from JSON Web Tokens and compares them against the requested object IDs before any database query even executes.
That makes a lot of sense. Only give access to what's absolutely necessary for that specific action. What about other layers? Any other defenses?
Yeah, you can definitely layer defenses. Utilizing an API gateway is a really good practice. It serves as a centralized enforcement point for things like rate limiting, which can significantly slow down those ID enumeration attempts we talked about. It can also help block known malicious traffic patterns before they even reach your backend services. Continuous testing is also crucial. Use automated tools, maybe something like OWASP Zeta, for fuzzing IDs, and conduct regular manual penetration testing specifically designed to simulate these privilege escalation attempts. And of course, robust logging and monitoring are essential. You need to log all access attempts and use security information and event management, or SIM, tools to detect anomalies and alert you to unusual patterns of access or rapid ID changes.
And for people using GraphQL specifically, are there any particular considerations here for preventing BOLA?
Yes, definitely. For GraphQL, you absolutely must implement authorization within your resolvers. You need per-field authorization checks. Don't just assume that if a user can access a certain query, they can automatically access all the fields it might return. You need fine-grained control there, too. NIST SP 895 also offers some good guidance on layering defenses, including things like data masking for non-essential fields to prevent accidental exposure even if authorization fails somewhere.
The prevalence of BOLA is truly, truly striking. What's the core insight here, the main thing our listeners should take away from this number one threat?
The core insight for Babel is this. Authentication gets you in the door, right? But granular authorization, right down at the object level, is what stops you from rummaging through everyone else's belongings once you're inside. Never, ever assume the client will only ask for what they're allowed to see. And critically, always verify object ownership or explicit permission on the server side for every single data access request. No exceptions.
Okay, moving from one fundamental authorization flaw to another, let's transition to API 2.2023 Broken Authentication. This is often called the weakest link in an organization's security posture, right? If BOLA is about what data you can touch, broken authentication is all about who you are. So what exactly does this vulnerability encompass?
Right. Broken authentication is fundamentally about improperly implemented authentication controls and, crucially, session management controls as well. It's the flaw that allows attackers to compromise authentication tokens, like session cookies or JWTs, or maybe exploit other weaknesses to simply impersonate other legitimate users. And if an attacker can successfully pretend to be someone else, especially someone with privileges, the consequences are obviously severe. They can gain partial or even full control over an API and its resources, leading directly to data leaks, system manipulation, unauthorized transactions, you name it.
This really sounds like the most foundational vulnerability. I mean, if you can't trust who's logging in or who's making a specific request, then all your other security controls become effectively useless, right?
Precisely. It completely undermines the very first principle of any secure system, reliably verifying identity. The core problem is that the API fails to correctly identify and verify the identity of the user or maybe the application making a request. It's alarmingly widespread, affecting something like 80% of audited systems in some reports. Its exploitability and detectability are rated as average, but the potential technical impact is definitely severe. This is particularly relevant for APIs because many modern APIs use stateless designs, for example, using JSON Web Tokens or JWTs. And these can actually complicate secure state tracking, making this risk even more pronounced if not implemented absolutely meticulously.
Okay, so how do attackers typically exploit these flaws? How do they bypass login systems or steal someone's identity? What are the common methods they use?
Well, there are several common and often highly automated methods. Credential stuffing and brute force attacks are incredibly prevalent. Attackers use automated scripts to rapidly try thousands, even millions, of username and password combinations. They frequently leverage huge lists of stolen credentials leaked from other data breaches. APIs that lack crucial defenses like rate limiting on login attempts or account lockout policies after too many failed tries are highly vulnerable to this. In fact, unrestricted resource consumption, which is API 4, we'll get to that shortly, can directly facilitate these types of attacks by allowing unlimited login attempts. Also with GraphQL, that batching capability where you can send multiple queries or mutations in a single request can actually exacerbate this by allowing potentially many authentication attempts at once, possibly bypassing simple per-endpoint rate limits.
Right. Yeah, I remember you mentioning that. For those less familiar, GraphQL batching lets you bundle multiple operations into one HTTP request. Great for performance, but as you said, it can inadvertently become a brute force supercharger if you're not carefully rate limiting the operations within the batch, not just the requests. What about session management? That seems like another really common area for attack.
Absolutely. Weak session management is a major vulnerability vector. This includes issues like exposing session identifiers and URLs, or using easily guessable session IDs that aren't cryptographically random, or maybe session IDs that don't expire properly, or worse, aren't invalidated immediately after a user explicitly logs out. These flaws allow attackers to perform session hijacking or session fixation, where they can steal or predict a valid session ID and then just impersonate the user, continuing their session without needing to re-authenticate at all.
I've also heard about something called MFA fatigue being used more and more frequently. Can you explain what that is and how it plays into broken authentication?
Yeah, MFA fatigue is a newer and, frankly, more insidious social engineering technique. While multi-factor authentication, MFA, is absolutely a crucial security layer, attackers have figured out how to overcome some implementations. They do it through social engineering combined with repeated push notifications. They basically spam a user with MFA approval requests, often late at night or when the user is likely busy or distracted. They keep doing it until the user, either annoyed or confused, just hits approve on one of them, simply to make the endless notification stop. And boom, they've inadvertently granted the attacker access.
Wow, that's incredibly clever from the attacker side and super frustrating for users. It exploits human nature. And what about just plain old hard-coded credentials? Is that still a problem in 2025?
Shockingly, yes. Hard-coded credentials remain a significant and frankly inexcusable security blunder. If an application's source code, or maybe a back-end deployment script, contains hard-coded admin credentials or API keys, then an attacker who somehow gains access to that source code, maybe through a repository leak or another vulnerability, can simply find these secrets and achieve full administrative access. It's like leaving the master key under the doormat.
Okay, this is where it gets really interesting and quite alarming when you see it in action. Let's look at some real-world examples. That 2022 Uber breach, for instance, sounds like a masterclass in chaining vulnerabilities together, starting right here with authentication.
It truly was a powerful and scary example of how multiple weaknesses can be chained together to achieve a full compromise. So, the attackers first purchased stolen Uber employee credentials on the dark web. Then, they used that MFA fatigue technique, the relentless push notification spam, to bypass Uber's multi-factor authentication. But once they were inside, they didn't stop there. They managed to find a PowerShell script somewhere on the network that contained hard-coded administrative credentials for privileged access management, or PAM, solution. That PAM system basically held the keys to the kingdom, providing a direct pathway to full administrative access to Uber's most sensitive internal services. This incident starkly highlights that just having MFA isn't a silver bullet. It needs to be implemented intelligently, using smarter methods like number matching, or at least limiting the number of push attempts allowed to effectively counter these fatigue attacks.
Wow, that's a really stark reminder that even robust security layers are only as strong as their weakest link, isn't it? And a compromised identity can just unravel everything else you built. Any other notable cases that come to mind?
Yeah, definitely. The 2020 Twitter Bitcoin scam is another high-profile example. In that case, attackers exploited weak internal tool API authentication to hijack numerous high-profile accounts. Think politicians, celebrities, major corporations. They then used those hijacked accounts to send out fraudulent Bitcoin scam tweets, netting millions in a short time. That involved credential stuffing on poorly protected internal endpoints. More recently, the 2022 LastPass breach, a major security company, involved significant API token mishandling, which ultimately allowed attackers access to customer password vaults. These examples, taken together, really underscore just how critical robust authentication and secure session management are. It's the bedrock.
Okay, so what can organizations actually do to prevent these kinds of breaches? It sounds like it needs to be a blend of using modern, cutting-edge technology and enforcing really rigorous policies and practices.
Absolutely, it's a multifaceted approach. First, strongly consider using a centralized OAuth server. This dedicated server should be responsible for issuing and managing access tokens and refresh tokens. It promotes consistent, secure, token-based authentication and helps enforce uniform access control policies across all your different services and APIs. Secondly, implement strong and modern authentication protocols. Adopt industry standards like OAuth 2.0, ideally combined with OpenID Connect, OIDC, for identity information. These are secure, scalable, token-based systems specifically designed for modern API ecosystems.
And what about the more traditional stuff, like password policies and managing sessions? Are those still relevant in this token-based world?
They absolutely are, and they're often areas where corners get cut. For passwords, if you're still using them for primary auth, you must enforce strong, unique passwords. And critically, store them securely using robust cryptographic hashing algorithms combined with unique salts for each user. Never ever store passwords in plain text or using weak hashing like MD5 or SHA-1. For session management, session IDs must always be long, cryptographically random, and transmitted securely, e.g. HTTPS only, secure cookie flags. Generate a new session ID immediately after a successful login to prevent session fixation attacks. And configure proper reasonably short session timeouts to limit an attacker's window of opportunity if a session token is somehow compromised. As for MFA, as we discussed, it's an essential extra layer, but advocate for and implement more secure forms than simple push notifications. Things like number matching, where the user has to input a number displayed on the login screen into their authenticator app, or even better, physical security keys like FIDO2 WebAuthn, are much more resistant to phishing and fatigue attacks.
Right. And those hard-coded credentials you mentioned earlier, the ultimate no-go.
Absolutely. Zero tolerance for that. You must implement secure secrets management. Never hard-code sensitive information admin credentials, API keys, database passwords, encryption keys directly into applications, configuration files, or source code repositories. Use dedicated centralized secrets management tools like HashiCorp Vault, AWS Secrets Manager, Azure Key Vault, etc. for secure storage retrieval and automated rotation of these secrets. Tools like Auth or Okta also provide managed authentication services that can abstract away many of these implementation complexities, which can be a good option. And OAuth's own authentication cheat sheet offers excellent, detailed, practical guidance for secure implementation if you're building it yourself.
Okay. What's the core insight about broken authentication? The one thing our listeners should really internalize from API 2?
The core insight for broken authentication is this. Your entire security posture, everything else you build, rests on the fundamental assumption that you actually know who is making each request. If that identity is compromised, if it can be faked, or if an attacker can simply walk through your front door using weaker stolen credentials, then every other security control you've painstakingly built essentially becomes irrelevant. Authentication is the unbreakable lock on your main gate. Any weakness there puts your entire kingdom at immediate risk.
Okay, let's move on to API 3.2023, Broken Object Property Level Authorization. Now, this is a new entry on the 2023 list, and it was formed by merging two older ones, excessive data exposure and mass assignment from the 2019 list. What exactly is this, and how does it differ from BOLA, the object level authorization we discussed first?
All right, this is a really crucial distinction, and it represents a more granular level of authorization failure. While BOLA, API 1, is about getting unauthorized access to an entire object that belongs to someone else. Broken Object Property Level Authorization, let's call it BOLA for short, is about a failure to enforce proper authorization right down at the individual object, property, or field level. So a user might have completely legitimate access to a particular object, say their own user profile object, but they shouldn't necessarily be able to see or critically modify all the data fields within that object. Think of it like having the key to get into a specific room, the object, but BOPA is like finding that all the locked drawers inside that room, the properties, are actually unlocked or can be easily forced open.
Okay, so it's about much more fine-grained access control, not just at the object level, but field by field. You can access the user profile object, but maybe you shouldn't be able to change the admin status field within it, or even see the payment token field. Is that the idea?
Exactly that. You hit the nail on the head. What's the common root cause for this kind of subtle but dangerous flaw? Well, the common root cause is often a failure to create and enforce explicit schema-based contracts for exactly what data can be sent to the API or received from the API for a given operation. Developers frequently fall into the trap of using generic methods, maybe in their ORM or data layer, that just return or update entire data objects. This inadvertently exposes potentially sensitive internal fields in API responses or allows unauthorized changes to restricted fields during updates. It's often more of a design flaw in how data is represented and accessed rather than just a simple coding bug like forgetting an if statement. It's rated as a common vulnerability, generally easy to exploit, and often easy to detect if you know what to look for. The technical impact is typically moderate, but the business impact can vary wildly depending on which properties are exposed or modified.
Okay, so how is this vulnerability actually exploited? You mentioned it consolidates two main attack vectors from the old list. Can you break those down?
Yeah, absolutely. The first vector comes from the old excessive data exposure. This occurs when an API endpoint returns an entire data object, or maybe just too much of it, without properly filtering out sensitive properties based on the specific requesting user's authorization level or context. Imagine an API that returns a user's public profile information, but the backend code just fetches the entire user record from the database and serializes it to JSON, inadvertently including internal fields like a payment token, internal adminets, maybe even hashed passwords or sensitive PII that shouldn't be there. Attackers simply use tools, like Burp Suite's proxy, to inspect the raw API responses. They look for this extra sensitive information, which might be hidden from the user interface, but is still present in the underlying data stream. OWASP provides a good example scenario involving a dating app where an API might inadvertently expose precise user locations or other private details that should obviously be kept confidential.
Right, leaking data that should have stayed internal. Okay, and the second attack vector, the mass assignment part.
Right, the second vector is mass assignment. This happens when an API endpoint allows a client, typically a user's browser or app, to update an object without adequately validating which specific properties within that object they actually have permission to modify. A really common vulnerable pattern here is when the backend code automatically iterates through all the key value pairs provided in the client's request payload, like a JSON body, and dynamically sets those attributes on an internal data object or database record. This is often done for convenience in frameworks. An attacker can easily exploit this by simply adding extra unauthorized fields to their request payload. They might add fields like user role, admin, or is blocked false, or maybe account balance, 100 to value. If the backend blindly assigns all provided properties, the attacker can effectively change values they have no right to change. Imagine an e-commerce platform where a customer could potentially modify a competitor's product price, but including the competitor's product and a new lower price in their own profile update payload if the backend isn't careful about which fields it allows to be updated through that endpoint.
Wow, okay, so you could potentially manipulate privilege data or grant yourself permissions just by crafting the right JSON request without having the actual privileges for it. That's pretty scary. What are some real-world consequences we've seen from these kinds of property-level authorization flaws?
Well, several significant breaches have been linked to these issues. Both the Pandora breach in 2018 and an earlier Uber breach in 2016 were connected to excessive data exposure, leading to the leak of millions of users' personally identifiable information, or PII. More recently, the massive 2021 Facebook breach involved property manipulation vulnerabilities, particularly within their GraphQL APIs, which ultimately resulted in the leak of data for a staggering 533 million users. These cases really highlight the severe, large-scale, real-world consequences that can arise from what might seem like minor design flaws in data handling at the property level.
Okay, so how do we prevent this? Beyond just, telling developers to be careful with what data they return or accept, this really sounds like a problem that needs to be addressed right at the API design and data modeling stage.
It absolutely requires rigorous validation and explicit schema-based control, ideally enforced from the design phase right through to implementation and testing. First, and maybe most importantly, you must enforce fine-grained authorization checks at the property level. Every single request that attempts to modify or even access an object property must be subject to granular authorization checks. Use RBAC or ABAC models that consider the user's role, the specific property being accessed, and the context of the request. Secondly, actively practice cherry-picking properties for exposure. This is essentially the principle of data minimization applied to API responses. Avoid returning entire data objects by default. Instead, explicitly define and return only the specific properties that are absolutely required for that particular business function or API call. Create specific data transfer objects, DTOs, or view models for each API response.
Right. So only give out the bare minimum necessary information, even in responses, to avoid those accidental data leaks.
Exactly. Don't just pass the internal database model straight through. Also, use schema-based validation for both requests and responses. Implement strong response validation using tools like JSON schema to define and enforce the exact data structure that your API should be returning. This acts as a safety net, ensuring only intended data is actually exposed, even if the backend logic accidentally includes extra fields. And critically, for preventing mass assignment, you must avoid dynamic property assignment. Train developers to avoid using functions or framework features that automatically bind all client input directly to internal object properties or database models. Instead, explicitly allow changes only to a predefined authorized allow list of properties for each specific update operation. Ignore any unexpected properties sent by the client. And finally, again, an API gateway can also provide a layer of centralized control here, potentially enforcing some of these policies at the edge by filtering requests that attempt unauthorized property modification or by validating response schemas.
This really sounds like a fundamental shift in how developers need to think about data handling in APIs. It's not just send the user object, it's send only the specific approved fields from the user object and validate everything coming in and going out. What's the core insight here for our listeners on API 3?
Yeah, the core insight for Broken Object Property Level Authorization is that even if a user is legitimately authorized to access a specific data object, they're almost never authorized for every single piece of data within that object. This vulnerability teaches us that trust, or rather authorization, needs to be applied at the lowest possible level of data granularity. We need to be meticulously filtering both what's accepted as input and what's exposed as output, field by field, based on precise permissions.
Okay, really clear. Next up on the list, we have API 4.2023 Unrestricted Resource Consumption. This used to be called Lack of Resources and Rate Limiting back in 2019. Why the name change, and what's the core issue here that makes it so dangerous in today's API-driven world?
The new name, Unrestricted Resource Consumption, I think better captures the broad range of negative consequences that arise from not properly managing API requests and the underlying resources they consume. It's fundamentally about the lack of proper rate limits, execution timeouts, payload size restrictions, query complexity limits, or other crucial resource restrictions on API usage. Without these controls firmly in place, an API becomes vulnerable to various attacks that can lead to a classic denial of service. Yes, but also potentially significant financial exploitation and just severe operational strain on your entire infrastructure.
Right, so it's not just about attackers trying to crash your own system anymore, but potentially about them deliberately costing you a lot of money or simply making your services slow and unusable for your legitimate customers.
It's exactly that. This vulnerability is particularly relevant and frankly quite dangerous today because modern applications and APIs frequently integrate with or heavily leverage third-party services. Think SMS providers, payment gateways, data enrichment services, AI models that are often built on a per request or per transaction basis. This makes excessive consumption a direct, tangible financial threat. Attackers can literally weaponize your own API to run up massive bills with these third-party providers. The core risk is that an API, which is often designed as a necessary public entry point, can inadvertently be turned into a weapon against its own infrastructure or, increasingly, against your company's budget. It's rated as a common issue. With average exploitability and usually easy detectability, you see the spike in traffic or costs. But it carries a severe technical impact and a varying, but often very high, business impact.
Okay, so how exactly are these vulnerabilities exploited? It sounds like the attacks themselves might be simple, but the consequences can be devastating.
They often are quite simple in concept. The most straightforward is the classic denial of service, DDoS, or distributed denial of service, DDoS attack. Here, attackers simply overwhelm an API with a massive flood of requests, often originating from large botnets, causing the API servers to become slow, unresponsive, or crash entirely due to resource exhaustion, CPU, memory, network bandwidth. Then there's a more targeted form of resource exhaustion. Attackers might craft specific, disproportionately complex or large requests. Think about deeply nested GraphQL queries that require joining lots of data, or attempting to upload extremely large files, or making requests that trigger computationally expensive operations on the backend. These carefully crafted requests consume an inordinate amount of server resources, leading to crashes or significantly degraded performance for everyone else. As we mentioned, GraphQL batching can also significantly amplify this type of abuse by allowing a single incoming request to trigger potentially many resource-intensive operations simultaneously.
So in these cases, the attacker isn't necessarily trying to guess an ID or bypass authentication. They're just trying to make the server work way too hard or maybe spend way too much money.
That's precisely one of the key attack vectors, especially the financial one. This leads to financial exploitation. This is where attackers deliberately make excessive, often automated calls to API endpoints that trigger actions involving third-party services billed per request. Their goal is purely to inflate your organization's operational costs. Imagine relentlessly abusing an SMS OTP, one-time password endpoint. Even if the OTPs are never used, each call might trigger sending an SMS message, each costing a few cents. Multiply that by millions of automated requests, and you can quickly rack up massive, unexpected bills from your SMS provider. And finally, let's not forget that brute force attacks against authentication, API 2, or enumeration attacks against object IDs, API 1, are greatly facilitated when APIs lack proper rate limiting. It allows attackers to make continuous rapid attempts without being blocked, significantly increasing the risk of compromise for those other vulnerabilities.
Right. So a lack of resource limits can make other vulnerabilities much easier to exploit, too. It's interconnected. This seems like a simple problem conceptually, just too many requests, but with incredibly complex and costly consequences. What are some real-world examples we've seen of this?
Well, the 2023 Twilio breach was notably linked, at least in part, to issues around API call volume overload, demonstrating the potential impact even on a major service provider that sells API services. Another really prominent, widely discussed case is the 2020 PS5 scalping bots. These bots notoriously exploited Sony's retail and inventory APIs for automated purchasing the moment consoles became available. These bots rapidly hoarded the limited supply of consoles. This not only led to significant resource strain on Sony's infrastructure due to the sheer volume of automated requests, but maybe more importantly, it caused massive business flow abuse, which touches on API 6 actually, and frustrated countless legitimate customers who couldn't buy a console.
Ah, yes, the scalping bots, a perfect example of abusing legitimate functionality at scale.
Okay, so what's the best defense against something that seems so fundamental to how systems interact online? How do you stop the flood?
Proactive limits and continuous vigilant monitoring are absolutely key here. First, and arguably the most direct defense, is to implement robust rate limiting and throttling. This is the most essential defense mechanism. You need to cap the number of requests a single user, an API key, or even an IP address can make within specific time windows, for example, per second, per minute, per hour. Throttling then complements this by delaying responses gracefully when limits are approached or exceeded, rather than just dropping requests, preventing the service from being overwhelmed. This should ideally be implemented at your API gateway, as close to the network edge as possible to stop excessive traffic early. Second, enforce strict quotas and usage limits. This is especially crucial for any monetized APIs or those that rely heavily on costly third-party services, precisely to prevent that financial exploitation vector we discussed. Set hard limits on usage over longer periods. Example, daily, monthly. Makes sense. Stop the flood at the gate, so to speak, and maybe also control the total volume coming out of the tap over time.
Precisely. You also need to monitor and analyze resource usage continuously. By establishing clear baselines for what constitutes normal API traffic patterns and resource consumption, CPU, memory, network I/O, third-party API calls, you can then use robust logging and analytics tools to quickly detect anomalies, sudden spikes, or unusual usage patterns that can indicate an attack or abuse, and trigger alerts. Strict input validation and standardization are crucial too, even for resource consumption. You must reject requests that don't conform to your expected schema, are excessively large PRG file uploads beyond a reasonable FIS limit, or contain overly complex, potentially resource-intensive queries before they even hit your back-end logic. Define limits on nesting depth, for GraphQL, for instance. Finally, on the back end, optimize your algorithms and data structures. Efficient code can naturally handle higher request volumes more gracefully.
Implementing caching, especially at the API gateway level for frequently requested non-sensitive data, can also significantly reduce the load on your backend services. And using container orchestration tools like Kubernetes or Docker allows you to set explicit resource quotas, CPU and memory limits, for individual microservices, preventing one overloaded service from impacting others.
Hmm. This one really underscores the importance of operational oversight and solid infrastructure design just as much as secure coding practices, doesn't it? What's the core insight here for API 4?
Yeah, the core insight is that every single API endpoint you expose, even those that seem completely benign or read-only, represents a potential drain on your finite resources. Without explicit enforced controls on how much of those resources can be consumed by any single user or system, you're essentially providing potential attackers with a blank check, whether that check is drawn on your computational power, your network bandwidth, or increasingly your actual bank account through third-party service costs. Assume malicious intent, or at least potential for accidental overload until proven otherwise, and put sensible limits on absolutely everything.
Okay, next on our list, we have API 5.2023 Broken Function Level Authorization. We've talked about controlling access to objects, BOLA, and properties within objects, BOPLA. What does function level authorization mean in this context, and why is it so dangerous when it breaks down?
Right. Broken Function Level Authorization, or BFLA, is the failure to enforce proper authorization checks at the level of specific functions, operations, or API endpoints. This means an attacker, often authenticated as a regular low-privilege user, can successfully access and execute functions or administrative resources that they are simply not authorized to use. They gain capabilities far beyond their legitimate role. Think of a standard user suddenly gaining the ability to access an administrative control panel, call a privileged API endpoint designed only for backend systems, or trigger functions intended solely for system maintenance or user management.
Okay, let me see if I have this straight. Booble API 1 is about getting access to the wrong data object entirely, like another user's profile. BOPLA API 3 is about touching the wrong fields within an object you might otherwise have access to, like changing the ISAdmin field. But BFLA is about accessing an entirely different type of capability or operation altogether, like calling the delete user function when you're just a regular user.
Exactly, you got it perfectly. BOLA typically focuses on horizontal privilege escalation, accessing another user's data of the same type as your own. BFLA, in contrast, is fundamentally about vertical privilege escalation, accessing a function, an endpoint, or a resource completely outside your normally permitted scope, typically one reserved for higher-level users, like administrators or internal systems. It allows attackers to perform highly privileged actions, changing critical application settings, deleting other users' accounts, modifying system-wide permissions, or initiating sensitive operations like triggering backups or shutdowns. It's rated as a common vulnerability, often easy to exploit once discovered, and usually easy to detect with proper testing. The technical impact is almost always severe because it grants unauthorized capabilities.
And what's the core security principle that APIs absolutely must follow here to prevent this kind of unauthorized capability access?
The absolute core principle, again, is the principle of least privilege. It applies just as much to functions as it does to data. An API must rigorously ensure that every user, every API key, every service account only has access to the absolute bare minimum set of functions, endpoints, and capabilities required to perform its specifically designated job or role, nothing more. Any failure here, any overly broad permission, leads to a complete breakdown of the intended security model and allows attackers to easily bypass intended access restrictions by simply calling functions they were never meant to reach.
Okay, so how do attackers typically exploit BFLA? It sounds like they're basically looking for hidden doors, maybe admin panels or internal functions that weren't properly locked down based on the user's role.
They are, quite literally, hunting for those unlocked doors. The attack typically begins with discovery of administrative or privileged endpoints. Attackers, often authenticated as standard low-privilege users, will systematically probe the API service to discover its full range of functions, looking beyond what the normal user interface exposes. They might do this by inspecting the client-side JavaScript code for hidden API calls, reading publicly available API documentation, which sometimes mistakenly includes internal endpoints, analyzing network traffic, or simply brute-forcing common administrative URL paths. They're looking for endpoints like APadmin delete user, a p-window settings update teal, a p an internal system reboot, or maybe just users make admin things that clearly shouldn't be accessible to everyone.
Right, and then once they find these potentially privileged endpoints, they just try calling them directly using their standard low-privilege user credentials or session tokens.
Exactly. This leads to the second critical step,
The lack of proper server-side authorization validation for that specific function. The attacker attempts to call the discovered privileged endpoint using their standard user credentials. If the server-side logic fails to adequately verify their permissions for that specific function or endpoint, maybe it only checks if the user is authenticated, but not if they have the admin role, then the API might wrongly return a 200 OK success response, or perform the action without error, instead of returning the appropriate 403 forbidden or 401 unauthorized error. This then directly leads to successful privilege escalation. The attacker can now perform actions normally restricted to higher-level users. They could potentially create a new admin account for themselves, delete a competitor's profile, change critical application settings, or manipulate system state, essentially becoming an administrator without authorization.
So it sounds like a lot of this comes down to that flawed security by obscurity approach, failing again developers, assuming that if an admin endpoint isn't linked anywhere in the regular user interface, it's somehow safe. That's just a fundamentally flawed strategy, isn't it?
It absolutely is. That's very often the root cause. Developers might add a new administrative function or endpoint and forget to explicitly secure it with proper role checks, operating under the dangerous assumption that regular users won't find it or know how to call it. But as we know, automated scanning tools, or even just a curious user inspecting the client-side JavaScript source code, makes discovery relatively trivial for anyone motivated. This is precisely why security by obscurity is never a valid or reliable security control on its own.
Makes sense. What are some notable real-world cases or scenarios where BFLA has led to significant security incidents?
Well, the 2019 Uber breach, which seems to be a recurring case study for multiple OWASP flaws, reportedly involved elements of function escalation as part of the larger chain of vulnerabilities exploited by the attacker. OWASP itself also describes a compelling hypothetical scenario where an attacker might be able to manipulate parameters in a user invitation process, perhaps guessing an endpoint for accepting invites, to trick the system into granting them an administrative role instead of a standard user role. These cases really underscore that even seemingly minor oversights in applying authorization checks consistently to every single function can lead to major systemic privilege escalations.
Okay, so how do we properly batten down the hatches against BFLA? What's the most effective defense strategy here? It sounds like it needs to be rigorous and applied everywhere.
Defense against BFLA really centers on rigorously applying that deny by default philosophy specifically to functions and implementing granular controls. First, and most effectively, you must implement fine-grained access controls at the function endpoint level. This means putting granular function-level access controls in place for every single API endpoint, meticulously tying access rights to specific, well-defined user roles or permissions. This demands robust application layer authorization checks on every single incoming request that hits any potentially sensitive function, verifying the user has the necessary privileges before executing the function's logic. Secondly, and maybe as the guiding principle, adopt a deny by default philosophy for all functions. This means every API endpoint should deny all access by default. Every private or internal API endpoint must explicitly require both authentication and specific authorization checks. Only truly public, unauthenticated endpoints, like maybe a public product catalog, the login endpoint itself, or account creation, should be exceptions, and even those need careful consideration.
Right, that's a powerful shift in thinking again. Instead of asking what functions do I need to protect, it becomes what functions do I need to explicitly allow access to and for whom.
Yes, exactly. It forces a deliberate security-first design process. Also, it's generally very good practice from an architectural standpoint to clearly separate administrative functions from regular user functions. Place administrative functions on entirely separate API endpoints, perhaps even hosted on different internal services or subdomains, with significantly stricter access controls, like requiring MFA reauthentication, IP whitelisting, etc. This reduces the attack surface exposed to standard users and minimizes the risk of accidental discovery and exploitation. Finally, security is not static. You need to regularly review and update your authorization rules. As your application evolves and new features or functions are added, your security policies need to keep pace to reflect current business requirements and close any potential authorization gaps. Always adhere strictly to the principle of least privilege. Continuous endpoint auditing, maybe using automated tools, is also key to catch any new or forgotten privileged functions that might have slipped through the cracks.
So function by function, role by role, explicitly define what's allowed and deny everything else.
Got it.
What's the core insight about Broken Function Level Authorization API 5 that our listeners should really take away?
The core insight here is that you must rigorously verify a user's entitlement or permission to perform a specific action or call a specific function, not just verify their identity, authentication. Don't ever rely on the user interface hiding privileged functions as your security measure. Assume that a determined attacker will find every hidden endpoint you have. Every single API function, no matter how seemingly insignificant, must be treated as a potential gateway to escalated privileges, requiring explicit, robust server-side authorization checks tightly coupled to well-defined roles or permissions before any action is taken. Okay, let's move to number 6. API 6.2023, unrestricted access to sensitive business flows. Now, this is a brand new vulnerability on the 2023 list, and it sounds really different. It seems like it's less about a technical coding bug like SQL injection or something, and much more about understanding the business itself. What exactly is this vulnerability, and why is it considered so critical now?
Yeah, that's a perfect way to describe it. This is a fascinating and important new addition to the list. This vulnerability doesn't necessarily stem from a traditional implementation bug in the actual code. Instead, it arises from a fundamental failure to properly account for how legitimate business logic embedded within your API functions can potentially be weaponized if it's used excessively, repeatedly, automatically, or in ways that go far beyond its intended scope or scale. Attackers essentially exploit these perfectly functional, legitimate business flows, think ticket purchasing, product commenting, user registration, to somehow harm the business itself, its genuine users, or its reputation.
Okay, hold on. So it's not necessarily a flaw in the API's code execution, but rather a flaw in how the business process itself was designed, or more likely, how that process was protected against large-scale abuse.
Precisely. You've nailed it. It's a vulnerability that's fundamentally rooted in the business design and the economic incentives surrounding a function, rather than just a technical coding error. Defending against it requires a security mindset that extends far beyond just secure technical implementation. It demands a deep understanding of the business context, the potential value an attacker might derive from abusing a flow, and identifying potential vectors for that abuse. Its prevalence is rated as common, but it's often quite difficult to exploit effectively, and even more difficult to detect reliably. Precisely because the individual API requests themselves often look perfectly legitimate according to the API's technical specifications. The direct technical impact might seem moderate, the API is just doing its job, but the ultimate business impact can be incredibly severe, including significant financial loss, like inventory hoarding or promotional abuse, massive reputational damage like spam flooding, and a severe degradation of service quality and availability for legitimate users.
Hmm. This sounds like a really sophisticated type of attack vector, one that requires attackers to deeply understand the application's purpose and its business rules. How do they typically exploit this? What does an attack look like?
It's often a multi-step, quite intelligent process, moving beyond simple technical probing. First, attackers perform reconnaissance and business flow identification. They carefully analyze the application to identify a legitimate business flow whose large-scale abuse would somehow significantly impact the company negatively or provide the attacker with value. Think about systems for purchasing limited edition sneakers or concert tickets, posting product reviews or social media comments, or maybe a user verification process that sends costly SMS codes, or even claiming promotional discounts. Then, once they've identified a valuable target flow, they move to automated abuse. Attackers write scripts or bots to automate this legitimate process at massive scale, overwhelming or exploiting the underlying business logic. This could manifest as those infamous ticket scalping or sneaker bots buying up all available inventory the second it drops. Or maybe botnets deploying endless spam comments on posts or products, overwhelming content moderation teams and degrading the user experience. Or perhaps flooding a user verification endpoint with requests for SMS messages, effectively causing a denial of service on a user's phone, or just running up huge costs for the company sending the SMS messages.
Right, so it's a feature that's meant to be used, perhaps even a core part of the business, but it's simply used far too much, far too quickly, or in an unintended, malicious, automated way.
Exactly. And beyond just overwhelming volume, more sophisticated attacks involve the direct exploitation of specific business logic rules for unfair advantage. For example, automating the process of claiming limited-time promotional offers or coupon codes faster than any legitimate human user possibly could. Or maybe exploiting flaws in loyalty program logic to generate points illegitimately. The nature of the attack isn't a typical technical bug that causes an error. It's often a feature working exactly as designed, just used maliciously at scale. This means the defenses need to be deeply embedded within or aware of the business context itself.
What are some real-world consequences we've seen from these kinds of business logic attacks? You mentioned the scalping bots.
Yeah, the 2020 PS5 scalping bots are probably the prime, easily recognizable example that falls squarely into this category. These bots exploited Sony's retail APIs to automate purchases and hoard consoles. This not only created significant resource strain, API 4, but more importantly, caused immense business flow abuse, API 6, by preventing legitimate customers from buying the product, leading to widespread public frustration and significant reputational damage for Sony.
Oh.
OWASP also describes common scenarios like automated social media comment submission that can quickly overwhelm platforms, drown out legitimate conversation, and severely tax their content moderation resources and infrastructure.
Okay, so what can organizations actually do to protect themselves against these business logic attacks? They seem to bypass many traditional technical security measures like firewalls or input validation because the inputs might be perfectly valid technically.
This truly requires a shift towards context-aware controls and robust behavioral analysis. It's a harder problem. First, you absolutely must identify and classify your sensitive business flows. This requires deep cross-functional collaboration, getting development, security, product management, and business operations teams talking to each other. They need to collectively understand the critical business processes enabled by each API endpoint and identify the potential risks and impacts if that flow were abused. Then, you need to implement context-aware controls that go far beyond simple, naive rate limiting, like just limiting requests per IP. You need controls that can recognize patterns of abuse specific to that business flow and build intelligence around typical versus atypical user behavior. Examples might include implementing stricter one purchase per user account, rules for high-demand items, deploying sophisticated behavioral analytics and machine learning models for bot detection, looking at speed, timing, mouse movements, etc., or maybe dynamically adjusting limits based on inventory levels or promotional activity. This requires a really deep understanding of your specific business logic and user patterns.
Right. So it's about looking much deeper than just the technical validity of the request. It's about looking at who is doing what, how much of it, how quickly, and comparing that against expected legitimate behavior, not just checking if they're technically allowed to make that single API call.
Precisely. Traditional access controls like RBAC or ABAC can still play a role here, of course, ensuring only appropriately authorized users can even access sensitive business flows in the first place. And you might even need to restrict legitimate users from performing actions that could harm the business if abused at scale, for example, limiting the number of views a user can post per hour. Regular security audits and specialized penetration testing are also crucial. These tests need to be specifically designed to probe and test the business logic by simulating these kinds of real-world abuse scenarios, uncovering weaknesses that standard technical vulnerability scans would definitely miss. An API gateway can also play a central role again, particularly in monitoring and controlling the volume related to these business flows, enforcing more sophisticated policies, perhaps based on user tiers or transaction history, and providing comprehensive logging and analytics specifically tailored to detect business anomalies. For particularly sensitive flows prone to automation, technologies like CAPTFI ages, though often user-unfriendly, or more modern invisible bot detection challenges might be necessary. And continuous dedicated monitoring of the performance and outcomes of specific critical business flows is absolutely essential to spot abuse early.
This one really emphasizes the need for security professionals to truly understand the entire business operation, the value drivers, the potential economic incentives for attackers, not just the technical stack. What's the core insight here for API 6?
Yeah, the core insight is that a perfectly functional, technically secure API, if its underlying business logic isn't adequately protected against abuse at scale, can actually become your greatest liability. It's no longer sufficient just to guard against technical bugs that cause errors. You now need to proactively anticipate and defend against the malicious orchestration and automation of legitimate features. You really need to start thinking like a potential business saboteur, not just a code debugger.
Very interesting perspective. Okay, let's turn our attention now to API 7 bot 2023 server-side request forgery, usually known as SSRF. This is another new entry on the 2023 list. What exactly is SSRF, and why is it considered such a dangerous and maybe growing threat in modern, often cloud-based architectures?
SSRF is considered critically dangerous, especially in cloud environments, because it provides a way for an attacker to effectively bypass an organization's carefully constructed network perimeter defenses and internal network segmentation. It occurs when an API includes functionality that fetches a remote resource based on a URI or URL supplied, at least partially, by the user without performing proper, strict validation on that user-supplied URL. The attacker can then craft a malicious URL that coerces the application, which usually resides safely behind the firewall on a private network, to send a crafted request to an unexpected internal destination. This could be another internal server, a database, a cloud metadata service, or any resource that should normally be completely inaccessible from the public internet.
Wow. So the server itself essentially becomes an unwitting accomplice, a confused deputy. It's tricked by the attacker into doing their bidding, accessing internal resources it shouldn't, effectively acting as a proxy for the attacker from inside the trusted network.
Exactly, that's the perfect analogy. The core mechanism is that the attacker manipulates a server-side function, like one that fetches an image preview, imports data from a URL, or calls a webhook, to act as an internal proxy. The server, often configured implicitly or explicitly to trust other services on its internal network, then dutifully makes the request to the attacker-specified internal resource. This internal resource might contain sensitive configuration information, expose misconfigured internal services, reveal internal network topology, or very commonly in cloud environments, provide access to sensitive cloud metadata or credentials. SSRF is rated as a common vulnerability, with average exploitability and detectability. The direct technical impact is often rated as moderate, but the potential business impact can be extremely severe, especially if it leads to credential theft or access to sensitive internal systems.
Okay, how exactly does an attacker typically trick the server into accessing this internal data? Can you walk us through a typical SSRF exploitation scenario?
Sure. The attack usually starts, like many others, with reconnaissance and endpoint identification. The attacker needs to find a vulnerable API endpoint that takes a user-supplied URL or part of URL and then uses it to make a backend request. For example, a legitimate request might look something like GAPE, APv1 product import image.url, http://www.example.com image.jpg, perhaps where the API fetches an image from an external URL to display it. Then the attacker moves to crafting the malicious request. They replace the legitimate external URL with a carefully chosen internal one. A very common and dangerous target, especially in cloud environments like AWS, is the internal metadata service. So the attacker might change the URL to something like gitty ab1 product import image.url http://169.169.254 latest metadata. This specific IP address, 169.254.169.254, is crucial because it's a special address used by AWS, and similar ones exist in other clouds, to provide metadata about the running instance to the instance itself. It's normally not accessible from the public internet, but it is accessible from within the instance running the API.
Ah, right. And the server, because it's just programmed to trust and fetch whatever URL is provided in that parameter, if validation is missing, just goes ahead and fetches that sensitive internal metadata without question.
Without proper validation, yes, that's exactly what happens. The server makes the request to the internal metadata service, or maybe localhost, or another internal server's IP address. It then often returns the sensitive data it retrieved back to the attacker, maybe embedded in an error message or directly in the response. This retrieved data could include temporary security credentials for the instance's IAM role, private IP addresses, application secrets stored in environment variables, or other sensitive configuration details. This then leads directly to data exfiltration and potential lateral movement. The attacker can use these stolen internal credentials, like temporary AWS keys, to directly access other internal cloud resources they shouldn't be able to reach, like misconfigured AWS S3 buckets, databases, or other services, and exfiltrate vast amounts of data. They can also use the SSRF vulnerability itself as a tool to perform port scanning of the internal network from the compromised server's perspective, identifying other potentially vulnerable internal services to target next.
So the server basically becomes an unwitting spy, poking around the supposedly secure internal network on behalf of the external attacker. That's a huge breach of trust. What's a prominent real-world case study of SSRF that really illustrates its danger?
The Capital One breach in 2019 is arguably the most significant and widely cited case study for the devastating impact of SSRF, especially in a cloud context. In that incident, the attacker exploited a misconfiguration in a web application firewall, WAF, that allowed them to execute an SSRF attack against an underlying server instance. This tricked the server into acting as a proxy, which then made requests to the internal AWS metadata service, successfully retrieving temporary internal AWS security credentials for the instance's role. Those stolen credentials were subsequently used by the attacker to gain direct access to and then exfiltrate massive amounts of data from, misconfigured AWS S3 buckets containing sensitive customer information affecting over 100 million individuals.
Okay, so what does this specific case tell us about cloud security? It seems like it wasn't fundamentally AWS's failure, but rather Capital One's configuration of their own services within the AWS cloud, right?
Precisely. That's a critical point. This incident perfectly highlights the shared responsibility model that governs cloud computing security. Cloud providers like AWS, Azure, or GCP are responsible for securing the cloud itself, the underlying physical infrastructure, the virtualization layers, the core network fabric. But the users, the customers like Capital One, are entirely responsible for ensuring the security in the cloud, that is, how they configure and secure their own applications, virtual machines, network access rules like security groups, BODFs, and data storage permissions. In this case, a user's failure to properly configure their way and rigorously validate user-supplied URIs in their application created the opening that led to catastrophic consequences.
Got it. So what's the effective multi-layered defense strategy against SSRF? How do we prevent attackers from turning our own servers against us like this?
Preventing SSRF requires a combination of strict input validation, network segmentation, and careful permission management. First and foremost, you must implement strict input validation on any user-supplied input that is used to construct a request URL. This is the most direct and critical defense. Use an allow list approach. Define exactly which domains, protocols, example only HTTPS, and maybe even specific URL paths your application is allowed to request. Vigorously reject any URL that doesn't match this strict allow list. Critically, your validation must explicitly reject any URLs attempting to access private IP address ranges like 10.xx, 172.16.x.x to 172.31.xx, 192.168.x.x, loopback addresses, 127.0.0.1 localhost, or special cloud metadata IPs like 169.254.169.254. Also, block requests attempted to use non-standard ports or schemes like file or gopher. Also, always enforce the principle of least privilege at the network level and for the service's identity. The API service itself should only have the absolute minimum necessary network permissions to reach the external resources it genuinely needs to function. Restrict its ability to access internal resources it doesn't explicitly require. Use network firewalls and security groups to enforce this segmentation.
Okay, what role does a web application firewall, WAF, play here? Since it was actually misconfigured in the Capital One case, how can it be used effectively?
A properly configured web application firewall, WAFer, can definitely be an effective layer of defense against many common SSRF patterns. You can configure WAF rules to specifically filter and block incoming requests that contain suspicious URLs or target internal IP addresses in parameters known to be used for SSRF. However, WAF aren't foolproof, as attackers can sometimes find ways to encode or obfuscate URLs to bypass simpler WAF rules. It shouldn't be your only defense. Continuous monitoring of outgoing network traffic originating from your application servers is also vital. Any sudden or unusual requests from your application servers to unexpected internal IP addresses, especially the metadata service or loopback addresses, could indicate an ongoing SSRF attack, and administrators should be immediately alerted. And finally, as always, patch and update your systems. The Capital One breach, as mentioned, was exacerbated by an unpatched vulnerability in the specific open-source WAF they were using, underscoring the constant need to keep all systems, frameworks, libraries, and infrastructure components up to date with the latest security patches. Also, a good practice is to avoid returning raw, unfiltered responses directly from the backend request your server makes. Parse and sanitize the response first, only returning the necessary data to the user to avoid leaking sensitive information even if an SSRF occurs.
This one really shows how a seemingly small configuration mistake or validation oversight related to URLs can potentially open up the entire internal network or cloud environment to an attacker. What's the core insight here about SSRF API 7?
Yeah, the core insight is that you can no longer implicitly trust any input, especially URLs, that guides your server's outbound actions, even if that action seems as simple as fetching a resource. You absolutely must treat any user-supplied URL component as potentially malicious, even when it's being used by your own trusted server. Your internal network perimeter is not inherently safe if your server can be tricked into acting as a proxy. An SSRF vulnerability effectively turns your server into an attacker's unwitting spy, completely bypassing the network boundaries that were designed to protect your internal resources. Validate everything.
Okay, let's move on to number 8. API 8.2 Valo 2023 security misconfiguration. Now, this feels like a classic vulnerability category, almost a catch-all that's been on security lists forever. But in the context of modern complex APIs and cloud environments, it seems to take on new dimensions of danger. What's the hidden flaw here that makes this so pervasive and critical?
You're right. Security misconfiguration is a perennial issue, but its impact is arguably amplified in the complex world of APIs and distributed systems. It fundamentally stems from the sheer complexity involved in correctly configuring APIs, their underlying servers, databases, cloud services, containers, CI/CD pipelines, and all the supporting infrastructure. It's very often the direct result of human error, maybe software engineers or DevOps engineers missing crucial security settings during setup, failing to consistently follow established hardening best practices, using insecure default configurations, or simply overlooking configuration details in the rush to deploy. These oversights inadvertently create wide-open entry points for attacks.
We're talking about basic but absolutely critical issues like leaving default administrator credentials active, like admin password, improperly configured cloud storage buckets, like making S3 buckets publicly readable or writable, accidentally exposing internal debugging endpoints or management consoles to the internet, forgetting to enable TLS HTTPS encryption on API traffic, implementing incorrect or overly permissive CORS, cross-origin resource sharing policies, or leaving verbose error messages enabled that leak internal details.
Right. So it's not necessarily a bug in the actual application code itself, but rather a fundamental flaw in how the code and its entire surrounding environment, the servers, the databases, the cloud services, the network settings, are actually set up, configured, and managed over time.
Exactly that. It's a widespread problem, often alarmingly easy for attackers to exploit once found, and frequently easy for them to detect using automated scanning tools. The potential technical impact is rated as severe, and the business impact, while varying, is typically high because a misconfiguration can often grant broad access. The real danger here is that a system might appear to be functioning perfectly from a business or user perspective, delivering the expected features, but still harbor critical, exploitable security flaws hidden just beneath the surface in its configuration. APIs, by their very nature of deliberately exposing functionality to the outside world, significantly increase the overall attack surface. And a single critical misconfiguration like that WF in the Capital One case or the Open API in the Optus case can unfortunately undermine all the other, perhaps well-designed security controls you have in place.
Okay, so how do attackers typically find and exploit these often subtle misconfigurations? It sounds like they might just be systematically scanning for common mistakes or low-hanging fruit.
They often are, precisely looking for those easy targets and common mistakes. Attackers use a combination of automated scanning tools like Shodan, Nessus, or specialized API scanners, and manual reconnaissance techniques to systematically scan infrastructure and probe for misconfigured systems and exposed API endpoints. They're actively looking for things like open ports, running services with known default credentials, publicly accessible cloud storage buckets, exposed administrative interfaces or debug endpoints that shouldn't be public, systems missing essential security patches, or APIs responding with overly verbose error messages. Once a potentially exploitable misconfiguration is found, they move quickly to exploiting it. This could be as simple as logging into a system using default admin credentials that were never changed and crucially lack multi-factor authentication. Or maybe accessing publicly readable cloud storage buckets to directly view or download vast amounts of sensitive company or customer data without needing any authentication whatsoever.
And what's the ultimate danger here? Can these misconfigurations really allow attackers to bypass other, stronger security measures you might have?
Absolutely. And that's often the most dangerous aspect and why it's ranked so high. The most critical security misconfigurations allow attackers to completely bypass other, often quite robust, security controls. The Capital One breach, which we've discussed extensively, is again a prime example. The misconfigured web application firewall effectively enabled the SSRF attack, API 7, which in turn allowed the attacker to gain internal AWS credentials. This rendered many other downstream security controls like network segmentation or database security essentially moot because the attacker was already effectively inside with elevated privileges gained by the initial misconfiguration. Once initial access is gained through a misconfiguration, data exfiltration can often go completely undetected for long periods if monitoring and logging systems are also poorly configured or not closely watched. Remember, in the Capital One breach, terabytes of sensitive customer data were downloaded from S3,
over a period of 76 days before the breach was detected. That's a huge prolonged blind spot caused initially by misconfiguration. OWASP also points to common misconfiguration scenarios like enabling log injection via improperly configured HTTP headers, which can allow attackers to tamper with crucial audit trails and cover their tracks.
Wow, 76 days undetected. That's
Yeah.
staggering. And what about the Optus breach again? Didn't that also boil down to a critical configuration error?
It did, fundamentally. The Optus data breach in 2022 serves as another powerful, simpler example of a fundamental misconfiguration leading directly to a catastrophic data leak. In that case, a specific API endpoint was simply left publicly exposed on the internet without requiring any authentication, apparently tied to a legacy customer management system. This basic misconfiguration, failing to enforce authentication, allowed anyone to simply enumerate sequential customer identifiers and scrape millions of sensitive customer records. It was a fundamental failure of implementing a basic deny-by-default security posture for API access. The more recent 2024 Movia transfer breach also notably stemmed from failures to apply patches and secure configurations in a timely manner.
Okay, so how do we possibly prevent these insidious hidden flaws? It sounds like it requires an almost overwhelming amount of vigilance across the entire technology stack.
Mitigation really requires a combination of automated hardening processes, continuous automated audits, and perhaps most importantly, a cultural shift towards security being everyone's responsibility. First, you absolutely must implement a repeatable, automated hardening process. This means having a consistent, scripted, and automated process for configuring all your environments, development, testing, staging, and production based on established security benchmarks, like CIS benchmarks. Automation is key here to minimize the inevitable human errors that creep in with manual configuration. Always remove or disable unnecessary features, default accounts, unused ports, and unneeded software components from your base images and deployments. Secondly, try to centralize your configuration management. Use tools like Terraform, Ansible, Chef, Puppet, or cloud-native configuration management services to manage and audit configurations across all your systems from a single source of truth. This ensures consistency and makes comprehensive auditing much more feasible.
Right. And clearly, ongoing checks, not just a one-time setup during deployment, are absolutely essential given how systems drift over time.
Absolutely essential. You must conduct continuous security audits and monitoring. Regularly review all your critical configurations, cloud storage permissions, firewall rules, API gateway settings, IAM policies, database security settings against current security advisories, best practices, and available patches. Use automated configuration scanning tools and vulnerability scanners continuously to detect drift from your secure baseline and identify newly discovered vulnerabilities. Critically, you need to enforce security by design, embedding security practices right into the development lifecycle. This is the core idea behind DevSecOps. Integrate security checks into your CI/CD pipelines, static analysis, SDMA, dynamic analysis, DAST, software composition analysis, SCA, infrastructure as code scanning. Security needs to be considered at every phase, from initial architecture design through development, testing, deployment, and ongoing operation. And finally, and arguably most powerfully as a preventative measure, implement a strict deny-by-default policy across the board. Every new API endpoint, every network port, every file share, every user permission should deny all access by default. Access should only be granted explicitly, based on proven need and proper authentication and authorization.
This truly sounds like it requires a massive cultural shift within development and operations teams, really seeing security not as a separate gate or checklist, but as an integral part of building and running reliable systems. What's the core insight here for our listeners about security misconfiguration at API 8?
Yeah, the core insight is that security misconfiguration is fundamentally a people and process problem, just as much as it is a technical one. It highlights that often the easiest way for an attacker to get into your systems is not through some incredibly clever complex exploit, but simply through an open door that was left unlocked due to an oversight, a missed step in a process, or an insecure default setting that was never changed. Your default configurations, your hardening process, your patching discipline, these are your absolute first lines of defense. Any deviation from a hardened, consistently applied deny-by-default posture is essentially an open invitation for attackers to walk right in.
Okay, well said. Next on the list, number 9, APZ 9.2023, improper inventory management. This sounds like a problem that only gets bigger and harder to manage as organizations scale up and adopt things like microservices. What's the specific danger of the forgotten API in this context?
Improper inventory management is an incredibly widespread yet often underestimated vulnerability. It arises simply from an organization's failure to maintain a comprehensive, accurate, and up-to-date inventory of all its APIs across all environments. As development accelerates, especially with microservices where teams deploy independently, organizations inevitably lose track of dormant APIs, maybe from old features, legacy APIs running on old infrastructure, internal APIs that accidentally become exposed, testing or staging APIs left running, or completely undocumented shadow APIs created outside of official processes. These might still be accessible, maybe even from the public internet.
Right. So these are APIs that maybe developers created for a specific, perhaps temporary purpose, like a quick test harness, an A/B test version, or an integration for a now defunct partner, and then just forgot about them. They never got properly documented or, more importantly, decommissioned.
Precisely that. And these forgotten APIs are incredibly dangerous because they're often completely unmonitored, unpatched against known vulnerabilities, and likely contain critical security flaws or lack modern security controls like authentication or proper authorization simply because they fell off the radar. They serve as silent, unmonitored potential entry points for attackers. Its prevalence is rated as widespread, simply because keeping track is hard. But detectability and exploitability are often rated as difficult for the organization itself because, well, you don't even know these APIs exist to test or secure them. Attackers, however, are actively looking for them. The direct technical impact might seem moderate initially, but the potential business impact can be severe if a forgotten API provides access to sensitive data or internal systems. The root cause is often the rapid proliferation of APIs, especially in those fast-moving microservices architectures. When independent teams are constantly deploying new services and APIs, maintaining a centralized, holistic view becomes incredibly difficult without strong governance and tooling. This inevitably leads to this dangerous phenomena of shadow IT, where APIs are created, used for a while, and then forgotten, but never actually taken offline or secured properly.
Okay, so how do attackers actually find these forgotten backdoors, these APIs that even the organization itself might not know about anymore?
Attackers are persistent and methodical. They use sophisticated API discovery techniques that go far beyond just looking at your official developer portal. They use things like DNS enumeration and scanning subdomains, looking for API-dev, test API, internal API, etc., analyzing historical web traffic logs if they can get them, monitoring certificate transparency logs, scraping client-side code from web and mobile apps, and simply brute forcing common API path patterns, v1, v2, staging tests across known domains. They're specifically looking for undocumented, unversioned, or deprecated API endpoints that might still be lingering online. Once they find a potential forgotten API, they move to exploiting the potentially unsecured API. These discovered legacy or dormant APIs often lack even basic security controls like authentication, authorization, input validation, or encryption, precisely because they were never intended for production or public access, or they predate current security standards and were simply forgotten during upgrades. The T-Mobile data breach a few years ago, for instance, was notably linked back to a misconfigured internal testing gateway that was accidentally left exposed on the public internet. Attackers found it and were able to use it to pivot into T-Mobile's internal network.
And the Optus breach again, was that also in part an example of a forgotten or maybe just poorly documented legacy API being left exposed?
Yes, the Optus data breach 2022 serves as another key example where a vulnerable API, which was reportedly tied to a legacy customer management system and seemingly forgotten or undocumented in terms of its public exposure and lack of authentication, allowed the massive extraction of customer records via simple enumeration. It highlights the risk of these forgotten assets. Attackers then use the access gained through these forgotten APIs for straightforward data exfiltration, as in the Optus case. Or, perhaps even more dangerously, they use them for lateral movement and persistence. A forgotten, unsecured internal API can serve as a perfect beachhead, providing attackers with initial access to the internal network they can then use to move laterally towards more valuable, perhaps better secured systems. And because these APIs are by definition unmonitored, attackers can often operate completely undetected for extended periods, causing prolonged damage before anyone even realizes they're there.
Yes.
OWASP also describes common scenarios like exposed beta hosts, unprotected password reset endpoints, or old API versions left running that fall squarely under this category. The 2022 LastPass breach, too, reportedly involved attackers gaining initial access via exploiting vulnerabilities in third-party software. potentially including undocumented or forgotten integrations that weren't properly inventoried or secured.
Wow. What's really fascinating here is how often the same underlying issues like forgotten assets, lack of basic authentication, misconfigurations keep cropping up across these different major breaches we're discussing. It really highlights the fundamental, almost timeless nature of these security problems, regardless of the specific technology involved.
Indeed. The patterns are remarkably consistent when you look closely, and they almost always point back to failures in fundamental security, hygiene, governance, and process.
Okay, so how do organizations possibly get a handle on their ever-expanding API sprawl, especially with microservices adding new endpoints constantly? This sounds like a massive, ongoing operational challenge.
It absolutely is a massive challenge, but it's solvable with discipline, tooling, and the right processes focused on the entire API lifecycle. First, you simply must build and maintain a comprehensive API inventory. This means establishing and diligently maintaining a single source of truth for all APIs across the organization, including internal, external, partner, dormant, legacy, and suspected shadow APIs. This inventory needs to include critical metadata like the API's purpose, its owner, its security posture, authentication required, data sensitivity, its current version, its deployment location, and its lifecycle status, e.g. active, deprecated, retired. Secondly, you need to adopt continuous discovery techniques. You can't just rely on developers manually registering APIs. Use automated tools that actively scan your network ranges, cloud environments, code repositories, and even network traffic logs to automatically identify new or previously undocumented APIs and immediately alert administrators or security teams when something unexpected is found.
Right, so you're always actively looking for things that might have slipped through the cracks, proactively hunting for those unknowns.
Exactly, you need to be hunting. And again, that foundational principle. Implement a deny-by-default philosophy for API deployment and exposure. Every new API created should ideally start with a default security posture that denies all external access until an explicit, authorized policy is reviewed and applied. This helps prevent accidental exposure of internal or unfinished APIs right from the start. Also critically, you need to enforce a robust API lifecycle management policy. This policy needs to clearly define processes covering an API's entire journey, from initial design and security review through development, deployment, versioning, documentation, monitoring, and crucially, formal deprecation and eventual retirement and removal. Proper versioning, clear communication about deprecation timelines, and systematic removal of old versions or retired APIs are essential to prevent zombie APIs. And finally, once more, centralize your API management, ideally with an API gateway. A gateway provides that single point visibility and control for managing, monitoring, and securing all your managed APIs. Enforcing a strict organizational policy that all API traffic must route through the managed gateway environment helps prevent attackers from bypassing your security controls by directly targeting unsecured, forgotten endpoints that aren't part of the official inventory.
This truly sounds like an ongoing, maybe never-ending battle against an ever-expanding attack surface, especially in those highly dynamic microservices architectures. What's the core insight here for our listeners about improper inventory management, API 9?
Yeah, the core insight for improper inventory management is brutally simple. You absolutely cannot secure what you don't know exists. Every undocumented, unmonitored, unpatched, or simply forgotten API lurking in your infrastructure is a potential wide-open backdoor into your organization that a determined attacker will eventually find. Comprehensive inventory management, continuous discovery, and disciplined lifecycle processes aren't just tedious bureaucratic governance tasks. They're absolutely fundamental to maintaining your security posture in a dynamic, complex, API-driven world. If it's running, you need to know about it and secure it.
Very clear. Okay, our final vulnerability on the 2023 list is API 10.2023, unsafe consumption of APIs. This is another brand new entry, and it addresses something that feels very modern and particularly insidious, the growing risk associated with software supply chains. What exactly is this vulnerability, and why is the simple act of trusting an API, even a legitimate third-party one, now considered a significant security threat?
This is a really critical new vulnerability, and I think its inclusion reflects the reality of modern software development. It directly addresses the significant supply chain risk inherent in today's applications, which are increasingly composed by integrating numerous external third-party APIs. We rely on these third-party APIs for everything from payment processing, mapping services and analytics, to weather data feeds, identity verification checks, and even core business functionality. The problem, the vulnerability, arises because developers often tend to implicitly trust the data received from these third-party APIs much more than they trust data coming directly from an end user. This misplaced or excessive trust often leads to implementing weaker input validation, standardization, or authorization controls for the data originating from these trusted third-party sources compared to user input.
Okay, let me see if I follow. So if I'm building an application and I integrate, say, a third-party address validation API, I might be super careful about validating and sanitizing the address fields submitted by my user in the web form, but I might not be nearly as careful about validating or sanitizing the structured address data that the third-party API sends back to me because, well, I inherently trust that external API provider. Is that the kind of scenario?
Exactly. That implicit, often unexamined trust becomes the very vulnerability itself. Attackers are increasingly aware of this and are actively targeting these integrated third-party services, not necessarily to attack the third party itself, but to use them as a subtle, indirect stepping stone to compromise the main target application that consumes their API. It's rated as a common vulnerability because integrations are ubiquitous. However, it's often difficult to exploit directly, as it requires compromising the third party first or finding a flaw in how the integration handles data, and it's even more difficult to detect because the malicious data or instruction appears to originate from a legitimate, trusted source on your network logs. The direct technical impact on your application might seem moderate initially, but the potential business impact can be severe if the attack succeeds. The core consequence is that a vulnerability or compromise in just one of your trusted third-party services can potentially cascade and compromise your entire system or steal your users' data. This starkly highlights the urgent need for a zero-trust security approach. Treat all incoming data, regardless of its origin, user or our third-party API, with suspicion.
Okay, so how is this actually exploited in practice? It sounds quite subtle and maybe difficult to trace back, as the malicious data is effectively being laundered through a trusted third-party source.
It is indeed subtle and often indirect. The attack usually unfolds in several stages. First, attackers perform reconnaissance to identify the third-party APIs that your target application integrates with. They can often discover these through analyzing network traffic between your app and external services, inspecting client-side code that makes calls to third-party SDKs, reviewing public documentation, or even just observing the features your application offers, like maps, payments, social logins. Then the attacker needs to exploit a weakness in the third-party API or service itself. This is the hard part for them. They need to find a vulnerability within that third-party service, perhaps an injection flaw, a misconfiguration, a data handling weakness, or maybe they compromise the third-party provider directly through other means. Let's say they find a cross-site scripting, XSS, vulnerability in a third-party review widget API.
Okay, so they've found a flaw in the third-party service you're using. How do they then use that weakness to attack your application?
This is the clever part. They use the trusted but now compromised or vulnerable third-party API to attack your target application indirectly. The vulnerability in the third-party API is leveraged to inject or send a malicious payload to your application when your application calls the third-party API. Your application, because it trusts the source, might not validate or sanitize the data received from the third-party API as rigorously as it would direct user input. For example, it might directly render HTML snippets received from the trusted review widget API without proper sanitization. This allows the malicious payload, like the XSS script injected into the review content via the third-party API flaw, to bypass your application's security controls that were primarily focused on user input. This can then lead to various forms of data manipulation or exfiltration within your application or against your users. In our XSS example, the malicious script injected via the third-party review widget API could then run in the browsers of your users when they view the reviews on your site, potentially stealing their session cookies or redirecting them to phishing sites.
The key danger here is that this type of attack often bypasses traditional security controls, like web application firewalls, WFs, which might be configured to trust traffic coming from known, legitimate third-party service IP addresses, making them effectively blind to attacks originating from those trusted sources. OWASP provides scenarios like SQL injection occurring because data received from a trusted enrichment API wasn't properly sanitized before being used in a database query, or open redirects happening because a redirect URL from a trusted identity provider wasn't validated.
The SolarWinds breach instantly comes to mind here again. Wasn't that a massive, devastating supply chain attack that propagated through trusted software updates and potentially API integrations?
Indeed, the 2021 SolarWinds breach serves as a prime, albeit complex, example of a major supply chain attack that leveraged compromised software updates distributed via trusted channels, potentially involving API interactions as well. It unequivocally demonstrated on a global scale how a weakness or compromise in one seemingly trusted component or provider could cascade catastrophically, compromising an entire network of highly sensitive systems and major organizations worldwide who implicitly trusted that component.
Okay, so how do we possibly defend against something like this, where the very act of trusting a necessary integration partner is what's being exploited? This sounds like it requires a fundamental reevaluation of how we build and integrate systems.
It absolutely requires a fundamental reevaluation of trust assumptions and a rigorous adoption of a zero-trust approach, even for internal and partner communications. Firstly, and most importantly, you must validate and sanitize all inputs, even those received from supposedly trusted APIs. Treat all data received from any third-party API as potentially untrusted, subjected to the same rigorous level of input validation, type checking, length limiting, and context-aware output encoding sanitization as you would apply to direct user input. Define and enforce strict data schemas or contracts for all incoming data, regardless of its source, and reject anything that doesn't conform. Secondly, more broadly, you need to enforce a zero-trust security model across your entire infrastructure and application architecture. The mantra here truly needs to become never trust, always verify. Services should not inherently trust other services, even those operating within the same internal network or owned by trusted partners. You need to authenticate, authorize, and validate every single interaction between services. This is especially critical in modern microservices architectures, where inter-service communication is constant and complex.
Right. So you're essentially saying assume breach everywhere. Don't trust anything implicitly. Verify everything all the time from everywhere, even from systems you think you should trust.
Exactly that mindset. You also need to actively secure your API integrations. Consider using a centralized API gateway, not just for exposing your APIs, but also for managing and securing all outbound calls to third-party APIs. This gateway can enforce consistent security policies, like mutual TLS, request signing, stricter timeouts, manage credentials securely, provide centralized monitoring and logging for all third-party interactions, and potentially perform some level of validation or transformation on the data exchanged. Also, don't forget to regularly audit and update the third-party services and libraries you consume. Keep track of security advisories for the third-party APIs you use. Regularly audit their security practices if possible. Critically, keep all your own frameworks, libraries, SDKs, and components that consume these third-party APIs fully up to date with the latest security patches, using software composition analysis, SCA tools, to identify known vulnerabilities in your dependencies. And finally, conduct regular security audits and penetration testing that specifically include scenarios simulating these real-world supply chain attacks. Testers need to examine how your application handles data from integrated APIs and look for ways to abuse that trust relationship. Additionally, where feasible, consider performing provider audits formally assessing the security practices, certifications, like SOC2, and track records of your critical third-party API providers themselves before integrating them deeply into your systems.
This final vulnerability really reinforces the idea that your overall security posture is only as strong as your weakest link. And increasingly, that weakest link might not even be your code or your infrastructure, but something external that you implicitly rely on. What's the core insight here for API 10?
Yeah, the core insight is that in our highly interconnected, API-driven digital ecosystem, your effective attack surface now extends far beyond the boundaries of your own code and infrastructure. It includes every single third-party service you integrate with. The moment you integrate a third-party API, their security vulnerabilities, their potential for compromise, effectively become your security risks too. Unsafe consumption of APIs, API 10, is a critical wake-up call for all organizations to adopt a rigorous zero-trust mindset for all data inputs and interactions. Recognizing that implicit trust in external services is no longer just convenient, it's a dangerous liability waiting to be exploited. Validate everything.
Wow. What a truly deep dive into the OWASP API Security Top 10 for 2023. We've really unpacked each of these 10 critical vulnerabilities. Before we wrap up, let's just quickly recap the overarching story that this list tells us about the evolving API threat landscape.
Indeed. I think it's clear the 2023 OWASP API Security Top 10 is far more than just a checklist. It really serves as a definitive roadmap for navigating the complexities of modern API security. The significant shifts we saw from the 2019 list clearly signal a maturing and frankly more dangerous API threat landscape. Attackers are becoming increasingly sophisticated. They're targeting not just the low-hanging technical flaws anymore, but are increasingly focusing on exploiting the very business logic that powers applications and manipulating the intricate inter-service communication patterns found in distributed systems like microservices. APIs have unequivocally become the primary attack surface for many organizations, a central, high-value target for malicious actors seeking data or disruption.
And what was that overarching truth, that recurring theme that just kept coming up again and again across nearly every single one of these top 10 vulnerabilities?
Yeah, a central, almost undeniable truth really emerged as we went through these. The major headline-grabbing breaches from Optus and Capital One right through to Uber and others resulted not from exploiting some hyper-sophisticated, previously unknown zero-day threat, but almost consistently from neglecting fundamental security hygiene, the basics. A single critical misconfiguration left unaddressed, a forgotten API endpoint left exposed without authentication, hard-coded credentials carelessly left in a script, unvalidated inputs blindly trusted, or improper authorization checks. These basic, often avoidable oversights create a direct, often trivially exploitable path right to sensitive data or critical systems. The simplest flaws often seem to lead directly to the most catastrophic failures.
Okay. So for our listener out there, maybe building or securing API-driven systems right now, what are the three key strategic principles they should take away? The core pillars for fostering a truly secure API-driven future based on everything we've covered today.
Yeah, I think we can distill it down into three absolutely essential pillars for any modern API security strategy. First, centralization and standardization, primarily achieved through implementing an API gateway. This isn't just about operational convenience or developer experience, it's a fundamental security imperative in today's complex environments. An API gateway acts as that single consistent point of entry, visibility, and policy enforcement for critical functions like authentication, authorization, rate limiting, input validation, and logging across all your managed APIs. This dramatically reduces the security burden on individual backend services, helps ensure consistent application of security best practices across your entire ecosystem, and crucially unifies monitoring and alerting to help spot anomalies and attacks faster.
Okay, pillar one, centralization and standardization via a gateway. What's the second key principle?
The second pillar is embracing security by design, underpinned by a strong deny-by-default philosophy. A reactive, patch-based security approach, where security is bolted on at the end, is simply no longer sufficient in the face of modern threats and rapid development cycles. Security must be a core, non-negotiable consideration right from the initial design and architecture phase of any API, woven into its very fabric. This demands a strong cultural emphasis on adopting a deny-by-default philosophy for access control at every level: network, function, object, property. Access to any resource or capability should be forbidden until it's explicitly and meticulously justified and allowed based on verified identity and permissions. This really requires a cultural shift within organizations towards a true DevSecOps mindset, where security is seen as a shared responsibility, integrated seamlessly into every phase of the development lifecycle, not just a final hurdle or someone else's problem.
Right. Security baked in, not bolted on, deny first. Got it. And finally, that crucial third pillar.
The third pillar is rigorous validation and comprehensive lifecycle management. This encompasses two key aspects. First, implementing robust, context-aware validation and standardization for all inputs, whether they originate directly from an end user or indirectly from another third-party API, as we saw in API 10. You must treat all external data as potentially hostile and untrusted until proven otherwise through rigorous checks. Second, this must be complemented by a continuous disciplined effort to build, maintain, and govern a truly comprehensive inventory of all APIs across the organization, actively discovering and managing, including dormant, legacy, internal, and shadow assets, API 9. This rigorous inventory and lifecycle management is essential to prevent forgotten or unmanaged APIs from becoming catastrophic, unmonitored vulnerabilities.
That's a really powerful summary. Centralize and standardize, design securely with deny by default, and validate everything while managing the full lifecycle. It seems the OWASP API Security Top 10 is really much more than just a list of vulnerabilities, isn't it? It's an urgent call to action for organizations everywhere. It forces us all to confront the reality that while exposing functionality through APIs is often a business necessity for innovation and connectivity, it fundamentally increases the organization's network attack surface, often exponentially. But by understanding these 10 critical risk areas, by internalizing these fundamental principles, and by addressing these risks proactively and systematically, organizations can move towards building a much more secure and resilient API-driven future.
And that ultimately has to be the goal for all of us involved in building and securing these critical systems.
Absolutely. So as we wrap up this deep dive into the OWASP API Security Top 10 for 2023, here's a final thought for you to consider. In a world increasingly built on layers upon layers of interconnected APIs, is your biggest security vulnerability the code you write yourself, or perhaps the code, the services, the APIs that you consume from others? And how do you ensure that the digital trust you necessarily place in your partners and providers doesn't inadvertently become your most dangerous digital liability? We strongly encourage you to take this list, review your own API development and security practices against it, and perhaps explore the official OWASP resources for even deeper dives and mitigation guidance. You can find them easily at owasp.org API Security. Thank you so much for joining us today on the deep dive.